This video, we will conclude our discussion of addition reactions to alkenes and alkynes that proceed via cyclic transition states. Okay, our learning goals, pretty much the same as the last one, except we're looking at some different reactions. We don't need to know the mechanisms for every single reaction we discussed today. For some of them, we'll only need to be able to use them in box problems, so providing the reactants, reagents, or products. But so I have that listed here, and you can check back if you need a reminder of which reactions you need to know the mechanisms for and which you don't. All right, awesome. So let's just start by you pausing and trying to recall just as many reactions to alkenes that proceed via carbocation intermediates, and then as many as you can think of that proceed via cyclic transition states. So you please pause and complete this exercise. Let's compare what I've sketched out to what you came up with. We'll start with the reactions that occur by carbocation intermediates. And we discussed as the starting material alkenes, alkynes, and dienes. And we'll start with alkenes. Let's think about I'm not going to list off the reactions because you've already learned them, but let's start to think about what they have in common. So they all proceed by a similar carbocation. And if this was an asymmetric alkene where the two carbons had different substitution, we would see Markovnikov selectivity. So I can change this figure a little bit. We would see the oxygen-based nucleophile adding to the more substituted carbon. So these reactions go via the most substituted carbocation. And so we get the most substituted product. We call that Markovnikov selectivity. For example, we would not observe any of the less substituted product. This one, the secondary alkyl halide. Okay, we also needed to be aware of rearrangements of carbocations. When we examined the reactions of alkynes, we saw that they had similar selectivity. We do see that the electronegative atom in these reactions is adding to the more substituted carbon. So we do get X, which is the more electronegative atom of the two adding to the two carbons of the alkene, adding to the more electronegative atom, in this case, two carbons of the alkyne. We said that these reactions are okay also for symmetrical internal alkynes, but you're going to have a product mixture when you use an asymmetrical internal alkyne. And then finally, for dienes, we had this possibility where HX could add in a 1-2 fashion versus in a 1-4 fashion, because those two double bonds are connected to each other. You can draw some resonance structures to prove that to yourself. And we discussed the kinetic via the most stable carbocation intermediate versus the thermodynamic, the more substituted and overall lowest energy product as determined by alkene stability. Cool, so that was the subject of last week. The subject of this week has been these reactions to alkenes that proceed via cyclic transition states. And the big difference is that there are no carbocations. So there are no carbocation rearrangements. There are also defined stereochemical outcomes as a consequence of the cyclic transition states and intermediates that we observed. For the cyclopropanation reactions, the two bonds to the carbene that adds, those two bonds are formed on the same side of the alkene. So it wasn't important to show stereochemistry here because these are achiral, but if we wanted to, we could show both bonds coming out of the page or going into the page to that carbon that came from the carbene and those cyclopropane intermediates or products. Finally, we looked at halogenation in the presence and absence of water and alcohol nucleophiles, and we saw this anti-addition of either the two halogens in the case of halogenation, or in the case of halogen formation, this anti-addition of bromine in the hydroxyl group. One thing to note is that if or for asymmetric alkenes such as this one, if we were to halogenate in the presence of water, we would observe Markovnikov selectivity, where the more substituted of the two atoms adding across those two carbons of the alkyne does add to the more substituted carbon. And this is not because it goes via carbocations, because it doesn't, but the intermediate does have some carbocation character, which drives the selectivity here. So we can think about the bromonium ion that has this positive charge on bromine. We discussed how the more substituted carbon of the two from the alkene, so we have secondary versus tertiary, that tertiary carbon, it shares the partial positive with bromine, and thus a nucleophile like water is attracted to that tertiary carbon. So we do see Markovnikov selectivity for asymmetric alkynes for the reactions that we learned, asymmetric alkenes for the reactions that we learned in the previous video. This is a good exercise for you, and then what you should also do is you should go back and name all the reagents and name all the functional groups. So for example, we could take a look at this transformation, and we could name that there's a halogen, and this doesn't have to be bromine, it could be chlorine or iodine. There's an alcohol, and that doesn't have to be methanol, right? The R group can vary. And then we have this 1,2, that vicinal haloether. So that's the functional group in the product, where those two carbons that are making the bonds to bromine and the ether group, they came from the alkene, and whatever R was, that's the alkyl group that you have on the ether. Okay, so you should go through and definitely do that. Let's move on to the new reactions that we're going to learn today. So just like alkenes, alkynes can be treated with elemental halogens. For alkenes, we observed addition of X2 across the two carbons of the alkene. What do you suppose we will observe for halogenation of alkynes? Yeah, something similar. So if we were to treat this alkyne with bromine, we would observe an anti-addition, just like we did for alkenes, of bromine across the two carbons of the alkyne. If there was another equivalent of bromine to add, we would observe an additional addition of bromine across those two carbons of the alkyne to get the final product. I have shown here a terminal alkyne undergoing this reaction, but it works just as well for internal alkynes. Doesn't matter if they're symmetric or asymmetric, since you're adding the same atom across both carbons, it works just fine for internal alkynes, symmetric or asymmetric. Cool. So if we had one equivalent of X2, in this case bromine, we would observe this 1,2-dihaloalkene product. It's the E isomer. And then if you were to add two equivalents of bromine, you would observe the, oh, this is fun, 1,1,2,2 tetra halo, in this case bromo, tetra bromo alkane. All right. You do not need to know the mechanism of this reaction. Let's look at a new reagent and a new reaction. That reagent is called metachloroperbenzoic acid. There's a lot going on with the name here. The meta part refers to this 1,3 relationship between the two substituents on the benzene ring. Benzoic acid, the benzoic acid part, that refers to this being a derivative of benzoic acid, which is this molecule. And finally, the per comes from the OO bond. So this molecule is metachloropurbenzoic acid, which we will hereforward abbreviate as MCPBA. And we can think about the HOMO and LUMO for this molecule. What do you think? I think the HOMO is easier than the LUMO. So for the HOMO, we have the non-bonding pairs of electrons on oxygen. And I suppose we have them on chlorine as well, but those are not going to be reactive. And then for the LUMO, we have pi star CO. We also have sigma star OO, and those will all be good acceptors. We have sigma star OH, so there's lots of possibilities for how this is going to react. Yes, and I do understand. One of those orbitals will be the absolute LUMO, but we've said before when there are several acceptor orbitals that are close in energy, sometimes it's hard to predict exactly what's going to happen. But what we can say is that MCPBA is going to use both its donor and its acceptor orbitals to interact with the alkene. You might ask, how would I know that? You know that because we're talking about it today. You wouldn't know that, but that's why we've organized these reactions in this manner. So it'll serve as an example of one of these electrophiles that has some acceptor that accepts electrons, and then a donor that donates back. Okay. Let's get to the fun part. The fun part is that treatment of an alkene with MCPBA, metachloropurbenzoic acid. Typically in a nonpolar organic solvent such as methylene chloride, will generate an epoxide. And just like for cyclopropanation, the two new bonds are made to the same face of the alkene because there just really is no other choice. You would not be able to make you cannot get your model kits out. You could not make a 3-membered ring where one bond is coming from the top and one is coming from the bottom. That is absurd. It will not work geometrically, at least not in a 3-member ring capacity. So we've generated an epoxide. Let's draw the complete curved arrow mechanism for how this reaction occurs. There's something important to point out is that the preferred conformation of metachloropurbenzoic acid is not how I drew on the previous page, which was like this. The preferred rotation around this single bond is actually to have the hydrogen pointed like that. And that's because there's this internal hydrogen bonding interaction between the partially negative oxygen of the carbonyl and the partially positive oxygen or hydrogen atom. So there's a hydrogen bond here. Why does that matter? Well, you will soon see. So let's try to draw out the alkene in this 3-dimensional representation. This is always so fun. All right. Yeah. And we're going to abbreviate aryl AR. So AR is the ring here. Now, what can happen is that, as you know, pi CC is electron rich. I'm just referring to the alkene here. and it will attack the LUMO of metachloroperbenzoic acid. So in this case, that LUMO is sigma star OO. If you expected it to be pi star, it is not. The sigma oxygen-oxygen bond is very weak, so it attacks sigma star OO. That breaks this oxygen-oxygen bond, and those electrons are going to pop down here and make a double bond between carbon and oxygen. That will have to break this double bond because you cannot have 5 bonds to carbon. But in a way, you can think about these electrons filling up pi star, if you would like. All right, that breaks the pi bond. Now these electrons are going to accept this proton and make an OH bond here. And then these electrons in the sigma OH bond, they are going to attack back. So that this is where we can see that 2 bonds are being made to this oxygen all at the same time. So that's generating these 2 bonds of the epoxide. No, well, you will know if I'm mad at you because I'll make you draw this on the test, but I'm unlikely to make you draw this mechanism on the test. So then why are we discussing it? We discuss the mechanism of this reaction because it helps us to understand the stereochemical outcome, and also because it's a nice demonstration of an electrophile using both its donor and its acceptor orbitals, and we can understand it. So it's difficult to draw out. There's a lot going on with the curved arrows, but you can do it, and it's good for us to understand this mechanism. All right, so then let's look at the byproduct of this reaction. The byproduct is this. I've tried to draw it in a similar orientation to how we had it over here. Okay, I'm gonna finish writing the homo-LUMO interactions. So the alkene, pi CC attacks sigma star OO. That broke sigma OO. Then we had the sigma OH coming and attacking pi star CC. This is our acceptor. All right, that was super fun. Let's get to the stuff that you are responsible for, which are predicting the products of these reactions, including stereochemistry. So stereochemistry here is important. The treatment of an alkene with a peracid, such as MCPBA, generates an epoxide. We should note that this reaction is stereospecific, meaning that different diastereomers of starting material yield different diastereomers of the product. So we see that trans 2-butene and cis 2-butene yield these 2 different products. So we have the methyl groups trans, their stereochemical relationship is maintained. And then for the cis-2-butene, the 2 methyl groups end up cis. Again, the stereochemical relationship is maintained. So why? Why does the trans alkene make a trans epoxide and the cis alkene make a cis epoxide? That's because the 2 bonds are made at the same time. The 2 bonds to oxygen are made at the same time. So there's no chance for any sort of bond rotation. There's no chance while those 2 bonds are being made for any sort of bond rotation, and so the stereochemistry is maintained. Let's just point out one more thing before we leave this page, which is that these epoxides are formed when they're chiral as racemic mixtures, and this is because the oxygen can add to either the top or bottom face of the alkene. I showed it here adding to the top face, but it could have just as easily added to the bottom face, and then you would get this product. Of course, these are the same because this is achiral, but when a chiral epoxide is formed, this matters. So for example, in trans 2-butene is undergoes epoxidation, it does generate a chiral epoxide, which will be formed as a racemic mixture. Cis-2-butene made a chiral epoxide, just like in the previous example, but I can assure you epoxidation happened to both the top and bottom faces of cis-2-butene. You just can't tell the difference between the two possibilities because they're the same. This is an achiral molecule. Now that we know how to make epoxides with MCPBA, we can remind ourselves all of the fun things that we can do with epoxides. They are incredibly useful synthetic intermediates because there are so many different ways to open them up because they are so unstable. So let's refresh our memory on one of those ways and let's draw a complete curved arrow mechanism for the formation of this diol from this epoxide. Be sure that you've tried yourself first, and once you have, let's go ahead and get started. So the first step when you're in a strong acid like this is to protonate the epoxide. Two reasons to do that. You're in strong acid and protonation is facile, but the other reason is that the epoxide itself is too weak of an electrophile to react with a weak nucleophile, such as water. But now we have the protonated epoxide. This is very electron poor, and it's a great electrophile. So from here, we can observe water attack the epoxide. Now, both of these carbons are the same, so we'll just attack one of them, and we'll attack this one. So when we do that, we are showing an SN2 occurring. So it is going to occur with inversion of stereochemistry. Okay, so we're going to end up with this intermediate. This intermediate is a protonated alcohol, and so it has a pKa of about -2. We will show that it's deprotonated by water to regenerate the catalyst and create the vicinal diol product. I've added stereochemistry here. I've assigned the absolute configuration so that you can first see the inversion, and then once you've inverted the stereocenter in the SN2, nothing changes, so that stereocenter in the product. Okay, and the carbon at which there is no reaction, there is no inversion, that carbon stays consistent the whole time with its stereochemistry. A little trick here is that this SN2, when the water adds, this is an anti-addition, right? Sigma star is behind, sigma star CO, which is being attacked, is behind the bond. So you end up with these with anti-hydroxyls. Okay, so we see anti-hydroxyls in the product. Also, you're going to preserve this anti-relationship of the alkyl groups, and you can see in the zigzag conformation they are anti. So that you can see that pattern going on here. But if you're ever in doubt, you just want to assign absolute configuration, and that will help you make sure that you have drawn the stereochemical outcome correctly. We should pause now and review all the ways that we know to open epoxides. So we looked at this one. We should think about all the other ways we know to open epoxides. Just do a quick brainstorm similar to what the exercise from the beginning of the lecture. This is what I came up with. Under acidic conditions, we will protonate the epoxide first, and then there's a weird SN2. So under acidic conditions, there's typically a weak nucleophile like water or an alcohol, and it's not strong enough to react with just the epoxide itself, like we saw in the previous example. So there's a proton transfer. The more substituted carbon shares the positive charge actually with the oxygen by having a long bond, just like we discussed for the bromonium ion in the previous example. And then when the weak nucleophile floats by, such as water, its electrons are attracted to that partial positive, and so we see opening at the more substituted carbon, which we call a weird SN2 because it doesn't usually SN2s happen at the less substituted carbon. So we can see the new bonds are formed at the more substituted carbon, and there is inversion of stereochemistry S to R. Now, under basic conditions, there are really good nucleophiles or decent nucleophiles, and they will just attack first. And what we have referred to as a normal SN2 reaction. So a normal SN2 reaction, which will happen at the less substituted carbon. So the new bonds formed are these bonds. And that means there was no inversion of stereochemistry at the stereocenter. So it stayed S. If for some reason there were stereochemistry at the less substituted carbon, then you would see inversions. But in this case, there wasn't, and the carbon with stereochemistry wasn't attacked at all, so it just stays. Its stereochemistry, its absolute configuration just stays the same. You can recall with the really basic nucleophiles, we needed to have a separate workup step. But for just mildly basic nucleophiles, we could include the proton source in the reaction mixture in the same step. Great, so you will want to review all of this moving towards the end of this class. Speaking of review, let's revisit the hydration of alkenes. This is one of the reactions that proceeds via carbocations. So please pause again and propose a complete curved arrow mechanism and predict the product of this transformation. We see triflic acid, it's a strong acid. As soon as it's put in water, it will generate hydronium ion. Hydronium ion will protonate the alkene. So the first step here is a proton transfer, or it's a proton transfer, but since it's happening to a pi bond, we call it an electrophile addition step. C1 is protonated here because that generates the more stable secondary carbocation. Now we do notice, however, warning bells, that this secondary cation is adjacent to a quaternary carbon. So we should predict a carbon shift, a skeletal rearrangement. So the electrons in that sigma CC bond, they fill up that empty p orbital on the cation. So this is a carbocation rearrangement, a methyl shift to be specific. And as you recall, that occurs to generate the more stable tertiary cation. There, okay. Make sure you're good with all of the implied hydrogens on all these carbons. I'm not drawing them all in, but just make sure you understand what went where. And now this tertiary cation is electron poor. We need to look for an electron-rich species. That electron-rich species will be water. We have no other choice. And it will donate electrons in a coordination step. This generates the protonated alcohol, which has a pKa of about -2. So we'll observe deprotonation with water to both regenerate the catalyst, which is acid, and the final alcohol product. So we observe hydration, or the addition of HOH across the two carbons of the alkene. But this happens with rearrangement. You might ask, is there any way to hydrate without rearrangement? So just do a straightforward addition of HOH across the 2 carbons of the alkene, just as you would do if you had an alkene that was not prone to rearrangement. So just as you would observe with an alkene that was not prone to rearrangement. Okay. Now, is there any way to do that for an alkene that is rearrangement prone because of the carbocation structure? Yes, chemists have solved that problem. So the solution to that problem is a great reaction called oxymercuration reduction. We don't need to be scared by it. We're going to go step by step through this reaction. So let's look at what we have. We have mercury 2 acetate. Acetate here, just to be sure you understand what that is. Acetate is the conjugate base of acetic acid, and it's the counter ion for mercury. We have water, and then the second step we have sodium borohydride. I cannot remember if you've seen sodium borohydride. I think I showed it to you as an electron-rich species at some point. This is a reductant, which is where the reduction part comes in. It is going to donate hydride. And we're not going to worry about the mechanism of that step. So we'll only be worrying about the mechanism of the first step, which we will look at now. You might say, I have no idea what's going to happen here, and that's fine. I get that. But remember, all of these reactions that we're discussing right now, and we have been taking some detours to review, but the new reactions, they all involve an electrophile that can accept electrons and donate electrons. And that's what we'll see here as well. So we will see that pi cc does attack sigma star HGO. So it attacks the sigma star orbital for the mercury oxygen bond. And the mercury has some d orbitals, so it has electrons on it that it can then donate back to carbon. So those are the 2 interactions that are observed. So pi cc attacks the sigma star orbital for the mercury oxygen bond and generating an acetate leaving group. I'll draw that out in a second because it breaks that sigma mercury oxygen bond. And then there is a non-bonding pair of electrons on mercury that attacks back. It attacks pi star cc. So we do have this cyclic transition state. And we will generate a cyclic intermediate. And that cyclic intermediate looks a lot like a bromonium ion, and it looks a lot like a protonated epoxide. And it is going to behave similarly to both of those things. So when I say it behaves like a protonated epoxide or a bromonium ion, what do you think that means? Yeah, it means that the more substituted carbon is going to share the positive charge with the heteroatom, or in this case, the metal. And thus, the more substituted carbon will be attacked by the electron-rich species. So we do have water here attacking the more substituted carbon. Okay, so this is an SN2, a weird SN2, where we have the non-bonding electrons on oxygen attacking sigma star for the mercury oxygen bond. Excuse me, the mercury carbon bond. We're breaking the mercury carbon bond. That generates an intermediate that looks like this. It's probably one of the most amazing things you've ever seen, right? You can guess it has a pKa of about -2. It looks like a crazy protonated alcohol. So it will be deprotonated by water. So there's a proton transfer step here. So we have the OH bond installed, and then we have this carbon-mercury bond. So this is the end of what you need to know. That's the end of what you need to know. For step 2, that will reduce off. So step 2 with sodium borohydride, that will reduce off this carbon-mercury bond and replace it with hydride. So it's called a reduction. And we do end up observing a product that results from the net hydration with Markovnikov selectivity, right? We did not observe this product. That would be the anti-Markovnikov product. We also didn't get any rearrangement. Yes! So we got the Markovnikov product because of this little bit of carbocation character in the intermediate. It's not a carbocation, but it has carbocation character. So that's why we got the Markovnikov product. Yes, we avoided rearrangement because although there was carbocation character, there are no full cations. So there's nothing to rearrange. I'm sure you're asking yourself many questions right now, one of which is, can an alkyne undergo oxymercuration? Yes, indeed. Yes, it can. So let's go ahead and predict what happens to an alkyne under oxymercuration conditions. You notice they're a little bit different than the conditions for an alkene. There is no reduction step separately from the oxymercuration. That's because there doesn't need to be one. I will do you a kindness. I will not make you, I want you so badly, but I will not make you learn how mercury interacts with the alkyne. But I think that we can all guess that the first set of steps here is hydration, right? So we're going to add HOH. It's going to hydrate the alkyne. What is the name of that functional group? That's an enol. So what do you think happens next? Are we going to isolate the enol? Nope. Under acidic aqueous conditions, which we are in, we will see tautomerization to form the ketone. It will form the constitutional isomer of the enol. This is still a hydration though, right? We've still added HOH across the 2 carbons of the alkyne. But we will observe this ketone product. I will not make you draw the mechanism for this part, so getting to the enol, but of course, you all know this mechanism for the enol keto tautomerization under acidic aqueous conditions, which you should practice right now, right? This video is not too long yet, so heck, let's do it together. We will protonate the enol with acid, either hydronium or acetic acid, either is okay. That will generate the protonated ketone. The protonated ketone will be deprotonated by water to generate the ketone. Easy peasy, lemon squeezy, as my 4-year-old says. All right, we can do that. Review the enol keto tautomerization if you need to. Now, a few more points that I wanted to make here. So there are other conditions for affecting this transformation. One of which is that we just talked about the brute force, treat it with sulfuric acid in the presence of water, the brute force method of generating the ketone from the alkyne. You could do that. I mean, look, oftentimes though, you don't want to just chuck sulfuric acid in with your very precious organic compound that you've spent many steps making. So, if you can avoid sulfuric acid, I say avoid it. So these are more mild conditions, certainly. So I would say the oxymercuration conditions are more mild than just chucking acid in. And sometimes you'll encounter mercury sulfate instead of mercury acetate as the reagent for oxymercuration of alkynes. And so that requires a little bit of sulfuric acid. So either of these sets of conditions are fine. So there's three possibilities for hydrating an alkyne to make a ketone. Those three possibilities are oxymercuration with mercury acetate, acetic acid, and water. Just chucking in some sulfuric acid and water, which is, like I said, that's a risk you want to take it. Or oxymercuration with mercury sulfate, mercury 2 sulfate, some sulfuric acid, and some water. So all three sets of conditions work perfectly fine. I'm sorry that there's three, but there are. So let's take a pause and summarize. We've learned 4 new reactions so far. Halogenations of alkynes. That's related to halogenations of alkenes from the last class. Epoxidation of alkene. Oxymercuration reduction of an alkene and oxymercuration reduction of an alkyne. So pause, fill this out, and then we'll continue in just a few moments. Let's compare what you came up with to what I came up with. Alkynes can be treated with elemental halogens. Chlorine or bromine really work the best for alkynes. To generate this 1,2-dihaloalkene in an E fashion, this goes by an anti-addition like you would expect because alkenes react with halogens via bromonium ions, resulting in anti-addition to them as well. 2 equivalents of X2 can generate the 1,1,2,2 tetrahaloalkane. I will not require you to know the mechanism for this reaction, but however, it's the same, similar to alkenes. I will point out that terminal alkynes as well as internal, both asymmetric and symmetric, are fine. They will just give one product. Convince yourself of that if you need to do so. Epoxidation of alkenes. Next up, an alkene can be treated with MCPBA or a generic per acid. I would like for you to actually specify a per acid, but if you just see RCO3H, that just means RCO3H. That means a generic per acid. Methylene chloride might be the solvent. Generates an epoxide in a stereospecific and stereoselective fashion. So the cis alkene will result in a cis relationship of the methyl groups in the epoxide, for example. Now things got really exciting with oxymercuration reactions of alkenes. The alkene can be treated under these conditions to generate the Markovnikov product. So if we're thinking about the 2 carbons of the alkene, we've hydrated across those carbons, adding HOH. The hydroxyl has added to the secondary carbon, not the primary one. So we've made the more substituted alcohol, the Markovnikov alcohol, without rearrangement. And that is the key here, one of the keys. There is no rearrangement because there are no carbocations. Finally, alkynes can also be treated under oxymercuration reduction conditions. They're slightly different. It doesn't require 2 steps. It doesn't require a reductant. You just need to add a little bit of acid. So we talked about there are other conditions as well that you can go look on the previous page for that. This does generate a ketone from adding the oxygen to the more substituted carbon of the alkyne. Okay, so this does form an enol first, which tautomerizes to form the ketone. And this is okay for internal alkynes as long as they're symmetric, but if they're asymmetric, they will give 2 different products, just as we discussed in that class last week, and you can go back and look at that if you need to. All right. Now, let's continue with our discussion of hydration. So in a hydration reaction, HOH is added across the 2 carbons of an alkene. We can imagine this reaction proceeding to make the more substituted alcohol. So the secondary alcohol, we refer to this as the Markovnikov product. Or we can imagine making the primary alcohol to generate the anti-Markovnikov product, the less substituted alcohol. Now, we know that acid catalyzed hydration, so if we were to take the alkene and we were to treat it with, say, an acid catalyst such as triflic acid, tosic acid, or sulfuric acid, in the presence of water, we would generate the Markovnikov alcohol via the most substituted, the tertiary cation, not the primary alcohol via the primary cation. Nope, doesn't happen. Their primary cations are too high energy. Now, let's say though, we just really need to make this primary alcohol. We really need to make it. How are we going to make it? Well, we can. I'm going to show you. But what can you say right away? Yeah, it will not involve carbocations. Yes, but it will not involve carbocations. In fact, we can achieve anti-Markovnikov hydrations via hydroboration oxidation reactions. So more fun reagents to learn here. Let's take this step by step. So we do have an alkene. We will generate, in this case, the primary alcohol. We can see overall, we've added HOH across the 2 carbons of the alkene, but this time, hydrogen was added to the more substituted of the 2 carbons of the alkene, and OH added to the less substituted. Now you know that there must be something new going on because we are not generating a primary cation. It is not happening. So let's take a look at these new reagents. So BH3 is called borane. We can draw the Lewis structure for borane, and it would look like this. Boron is sp2 hybridized, meaning that it has 3 sp2 orbitals with which it makes sigma bonds, and a p orbital, and that p orbital is Mg. You will notice that there's THF. THF is the solvent for this reaction. You do need to specify it. There are very few times in my class that I make you specify solvents. This is one of those times. Let's draw out THF. I'll draw it right here. THF stands for tetrahydrofuran. It is this solvent right here. It's a really common cyclic ether solvent. Ethers are pretty inert, meaning they don't react, and they're pretty common solvents. So THF, it actually coordinates. It means it sort of donates its electrons to the empty orbital on boron. And it's required. So when you buy borane, it's as a solution in a coordinating solvent that stabilizes the electrons on THF, but we think about it stabilizing borane. Otherwise, this empty orbital, it's a super good acceptor. It'll accept electrons from wherever, and then you won't have it to do the reaction you want it to do. So sorry, I'm getting in the weeds here. So let's go ahead and look at what happens when you treat the alkene with borane. So we will have pi CC attacking. So pi CC is a donor. What do you think it attacks on borane? Yep, it attacks that empty p orbital on borane. So that's the acceptor. Now we know this entire unit, and again, we've done a lot of reviewing and deep thinking today, so it's easy to lose track. But we're talking about electrophiles that have donors and acceptors. So what is the acceptor for the donor for borane? Yeah, you have no choice. The only electrons borane has are those sigma BH electrons. So we see pi CC attacks boron, and then boron donates its sigma BH electrons to pi star CC. That generates an intermediate that looks like this. And so we've done it, folks. We have put the hydrogen on the more substituted carbon. We've been trying to do this, for the last 2 weeks. We finally have done it. I just took this new reagent. Now, some of you are wondering, why does that happen? I'm going to tell you. If you don't want to know, you skip ahead a little bit until you skip ahead till you start seeing me drawing more stuff. So, all right, why does hydrogen add to the more substituted carbon here? Well, it's because in this transition state, the carbon that doesn't make the bond to boron, so this carbon, it has a little bit of positive charge on it, and that little bit of positive charge is most stable on the more substituted carbon. This is a video, so I suppose you could rewind, but I will say it one more time. In the transition state, one of the carbons is bonding to boron. The carbon that is not bonding to boron, it gets a little bit of positive charge on it. Where is that positive charge most stable? Yes, on the more substituted of the carbons of the alkene. Thus, the less substituted carbon bonds to boron, and the more substituted carbon has that teeny tiny partial charge for just a second, and then it accepts the electrons from hydrogen and makes this carbon-hydrogen bond. So you can see, like, even though we're making the anti-Markovnikov product, all of this can be explained by carbocations. You can understand all of it if you just understand carbocation stability and want to think for a second. Cool. Those of you who skipped the explanation, you can come back. We want to think now about how we're going to replace the carbon-boron bond with a carbon-oxygen bond. And that happens by step 2. That's an oxidation. Oxidation. And I don't need you to know the mechanism. I do need you to know this mechanism for step 1. It is only one step. I trust that you can handle it. You can look up the mechanism for step 2, though. It's not that challenging. You can definitely understand it. Let's not learn things that aren't crucial. So you're not responsible for it. Let's move on to alkynes. So what are the conditions that you know of for hydrating an alkyne? Well, you can pause. We've learned oxymercuration. Oxymercuration will generate the ketone, and this happens via the enol. So we have this Markovnikov selectivity. There's some carbocation-ish stuff involved, and so we have this Markovnikov selectivity. The enol then tautomerizes under the acidic aqueous conditions to form the ketone. And then we discussed there are some other ways to do this, affect this same transformation. You can just hit it with sulfuric acid, but like I said, that's usually not the best idea. or you can use mercury 2 sulfate. You'll also need a little bit of sulfuric acid and water. All right, so what is the selectivity of bond formation, and what is the final functional group in the product? The selectivity is Markovnikov. We form the more substituted carbon forms the bond to oxygen. And the final functional group is a ketone. But you guessed it, my next question is, well, what if we wanted the opposite selectivity? What if we wanted to hydrate, where this time oxygen is making a bond not to carbon 2, but to carbon 1? How would we do that? And what would happen if we could do that? I mean, this is an enol. What would that enol do? It would then tautomerize to generate a functional group we have not been able to make yet, the aldehyde. Can we do it? Yes, yes we can. And that will be with hydroboration oxidation, but this time of alkynes. Now we have a slightly different reagent here, 9-BBN. 9-BBN stands for 9-borobicyclononane. This little guy, that's super fun to draw. You can do that in your spare time when you get bored. You could also use diisoamylborane. Sometimes you see this reagent. The key here is that it's a bulky borane and there's only one BH bond. So sometimes these might be abbreviated as R2BH, where R is bulky. And we'll talk about that in just a moment, why that might be that we need a different reagent. So let's go ahead and look at the mechanism here for the hydroboration of alkynes. It will be really similar to the mechanism for the hydroboration of alkenes. So we will have the pi CC donating to boron, and then the sigma BH donating to pi star CC for one of the double bonding interactions between the two carbons. See if you can draw the product of this elementary step. Yeah, so the product looks like this. And oops, but it's R. And then what would you say about this? I mean, this is an alkene, right? This is an alkene. So this, if you used borane here, this would just keep reacting with borane. Borane is small, it'll get in there, it'll hydroborate the remaining double bond. But when you have these really bulky R groups, like you have these huge, I don't even know what to call them, rings. I mean, when you have these huge R groups, or if you have these bulky R groups, yeah, this is like, what are we at? An hour long video now. Those big R groups block the alkene, really, from continuing to react with more BH bonds. We don't want that to happen. Cool. So then we have step 2. That's the oxidation step. That generates this intermediate. Okay, so we have an enol. And now the enol can continue reacting because we're in basic aqueous conditions, right? So we know that under basic aqueous conditions, the enol will tautomerize to the aldehyde. Let's quickly take a look at that tautomerization. So we're going to deprotonate the oxygen. We know that that OH is not in the product. So deprotonate that oxygen. We're in base, deprotonate something. Now we need to protonate the alpha carbon. No problem, we can do that. Reform that nice strong CO double bond. Protonate the alpha carbon. In basic aqueous conditions, the acid is water, so use water. And that will generate the aldehyde product. Okay, awesome. So what are the similarities and differences between hydroborations of alkynes and alkenes? Well, we needed to use this bulky reagent to avoid multiple reactions. Right? We know that alkenes have 2 pi bonds. We only want to react with one, so we use that bulky reagent to avoid 2 reactions. In both cases, though, we get the same selectivity. We get this anti-Markovnikov selectivity. So we have the oxygen adding to the less substituted carbon. So that's the same between both of them. And let's just make that super clear by drawing out the enol. Right? So we can see how similar the enol looks to the product of alkene hydroboration. We have the oxygen, the OH, bonding to the less substituted carbon. Okay, so that's a similarity between them. The difference would be we have to use that bulky 9BBN to avoid multiple reactions because there are 2 pi bonds. Let's summarize hydroboration reactions of alkenes and alkynes. Haha, I've done it. Something that I should point out to you, and I was going to point it out in the practice problems, but I'm going to save the practice problems for a separate video because this one is going so long. I want to point out the stereochemistry of hydroboration. The H and OH that are added by hydroboration, they add in a syn fashion. So for example, if we had cyclohexene, let's do methylcyclohexene, and we treated it under hydroboration conditions, what we would see here is that the product would have the hydrogen and the oxygen that added in hydroboration, they add to the same side. So you will not see any other diastereomer of the product. This one is formed as a racemic mixture. But for example, you would not see the methyl group and the hydroxyl syn to one another because the H that adds and the OH that add, they add syn. And that's because the bonds are formed at the same time. So when you think about the hydroboration oxidation mechanism, let's do it right here. Okay, so when you think about this mechanism, the bonds, the carbon boron and the carbon hydrogen bonds, they are formed at the exact same time. It's called a concerted mechanism. They're formed at the same time. And so because of that, you have this syn relationship. And remember that the boron, the BH2, that becomes the OH. So that's why after oxidation, the OH and the hydrogen, they're still on the same side of the alkene. Okay, so that's important. That stereochemistry is really important to keep in mind. Okay. And then again, it doesn't have to be 9BBN. This has to be something bulky. So in my practice problems, you might see R2BH. You might see diisoamyl borane. I showed you that one as well. Okay, you guys got it. So there's a bunch of practice questions. Eventually, I will upload a video of the solutions, but the solutions are already in these notes, so you can check those out. Be sure to reflect. Be sure to practice. Remember, just learn the mechanisms that I explicitly showed you and stated you needed to know, and those are listed here. Okay.